Thank you. My name is Johnson A. Asumadu at Western Michigan University as faculty, Kalamazoo, Michigan. And my partner is Brian J. Krug, faculty at Grand Valley State University, Grand Rapids, Michigan. Our topic is magnetic nanoparticle-based gyroscopic sensor. Now, take the evolution of gyroscopes. What is shown here are three basic gyroscopes. We have the mechanical gyro, the laser gyro, and then we have the MEMS gyro. Of course, the mechanical gyro depends on the magnetic field orientation. The laser also depends on the magnetic field orientation, but it has got lasers and mirrors to get a better accuracy. And the MEMS are more like capacitors, so they measure capacitances depending on the orientation of the capacitances. Now, let's look at a concept that we have in our invention. Now, consider the nanoparticle sitting down there. The rotating axis of the nanoparticle is Z, but if for some reason the orientation axis changes to S, that orientation change induces force. And then, of course, the force is accompanied by torque. And the torque creates precession or wobbling about the axis, the Z-axis. Now, our invention tried to realign the axis back to Z through what you call the new vector technique. Basically, what it does is that it takes the wobbling realign it, the spinning of the particle to the new field vector. Consider this enclosure of non-conducting fluid. Now, we have a magnetic nanoparticle suspended in the fluid, and we are using ethylene glycol. As it is, the nanoparticle is suspended in the solution. Now, if you look at the Brownian motion, if the nanoparticle is less than a certain nanometers, it doesn't settle. It stays suspended in the fluid. Now, consider the two conductors, conductor 1 and conductor 2. Conductor 1 carries current sine omega t, and conductor 2 carries current sine omega t, except the conductor 2 current is 90 degrees out of phase with that of current I1. Similarly, the space angle between the two conductors are 90 degrees. And this is right, according to Tesla, you could produce a rotating AC magnetic field. And so effectively, these two conductors with these two currents, 90 degrees out of phase in current, 90 degrees out of space, free space, will create a rotating magnetic field of speed omega. And therefore, the nanoparticles will be forced, the nanoparticle will be forced to rotate at that speed or frequency, omega. Let's look at a container containing so many nanoparticles. They all be spinning at the frequency of the magnetic speed rotation of the magnetic field. And the rotation, we can look at each individual nanoparticle as a single electric motor. Now, but they will be kept spinning in the axis of rotation of the magnetic field. So the magnetic field now has control over the rotation of the nanoparticles. And don't forget that the nanoparticles are also magnetic. Now, this is what we did. We took the case, we wrapped conductors around it, windings. What you see, we have two windings, the black one, and then the blue one around the enclosure of the container. You have the nanoparticles solution in there, and they are closed And then the first coil carries AC current, and the other second coil carries AC current, the same magnitude, except it's 90 degrees out of phase with the first coil. Now, this produces a rotating magnetic field. Therefore, it forces the nanoparticles to spin the same frequency as that of the rotating magnetic field. Supposing changes occur in the orientation, for example, if the enclosure is rotated or is turned or for some reason is moving for some reason, the nanoparticles will be oriented in different the axis will change, causing precession. And because the nanoparticles are being forced to rotate in the same direction and in the of the magnetic rotating field, effectively, any changes will cause perturbations in the input current. That's exactly what is going on here. You rotate the enclosure, the nanoparticles become disoriented, they wobble, but because of the magnetic field moving with a specific axis, the nanoparticles will be forced to spin in that axis, and therefore there will be perturbations in the input current. Now, this is sample construction, very simple construction. Very simple construction. It's made up of just the container, and then what you have in the container, you have two windings. On top of it, this is one winding set, and then the other winding is below this one here. This is one of the terminals. The other terminal is somewhere here. And so now that's where we apply the AC signals. Now, we did a simulation to find out the flux pattern in the produced by the two windings, and we found out that we have a lot of leakage. All the blue lines are leakage flux, but the useful flux are the green ones. At least we know we're getting some useful flux in the enclosure, which is very good, although we are losing a lot of flux. But the good thing is that the enclosure is non-conducting. Now, this is our experimental setup. We have the nanoparticle container sitting down here. We have a motor connected to that so that we can rotate it so that we cause wobbling in the nanoparticles. We have a signal generator. We took the signal generator, split it into two, and AC into two, and then we feed one winding with one phase, and then the other winding with the other phase. And of course, we put a capacitor in the other phase so that the currents in those two windings will be 90 degrees out of phase. And of course, we have all our measurement instruments attached to study the behavior of the nanoparticles if we have rotation coming from the motor here. We use the motor to do the rotation. This is our test bed. This is the nanoparticle, the prototype sensor, and then this is a turntable, and then this is our setup. We can rotate the turntable at from 2 hertz to 20 kilohertz, slow speed to very high speed, and of course the behavior of the sensor is observed. We know that when the table is oscillating at a certain frequency, we observe that the sensor output voltage changes. It changed. Now, when the turntable came to standstill at a stop position, this is the output voltage. And so we know that we are getting some output voltage from the sensor when the turntable was oscillating. And we are not claiming that we have a product, but we need to do more of this. And to move ahead, what we did is we refabricated our sensor. A company in Michigan, Podomatic, redesigned our sensor for us, and you have a container, and then the windings are inside the container here. Now, the advantage here is that we reduce the flux leakage, and also we make sure that we reduce the electromagnetic interference from outside. And so that works very well for us. This is the sensor in the form when it's closed. Of course, these are the conductors, the 4 conductors coming from the sensor. Very simple to fabricate. And we make sure that we made it more sensitive. Now, this is our setup in the lab. We have the sensor sitting on the turntable, and this is our setup. And we set all this up with little funding. You know, we got 10,000 here, we got 5,000 here. We put together, and we're able to set this one up. However, we need to do about 6 months of intensive data collection with different concentrations of the nanoparticle solution. And also, we designed more than one sensor so that we could see the behavior of the sensor under different fluid nanoparticle concentrations, and also the different size of the nano sensor itself to see whether our product will be viable. Now, we got funding from NSF to attend the NSF ICOP program, discovery program. And through this, we learned several things. We learned the parameters that are very important to the industry. And the parameters are scale factor, size stability, G2 sensitivity, bias stability. The bias stability is also known as the random walk, the bandwidth, and the bias repeatability. And of course, other parameters confirmed by the experts in industry. We talked to several companies, several experts, and we did about 200 interviews. And through this, we learn about these parameters. Also, we are going to concentrate on the first 3 sets of parameters. Also, through the NSF ICOP Customer Discovery Program, we also learn who our customers are, who use this type of customers, who use this type of sensors. And then we also learn where these sensors are used. Now we can, we learned that there are 3 basic areas where the sensors are used. We have what they call the commercial grade sensors, we have the industrial grade sensors, and then we have the military grade sensors. And so this program was very useful in showing us where our product is needed. For example, we didn't think that this sensor could be used by drilling companies, but we found out that this is one area where our sensor will be very, very useful, drilling. Now, the sensor is very simple to fabricate it. It doesn't mean it's just simple fabrication. Of course, when you do small parts milling, drilling, and screw together stuff, it's more difficult. But the principle behind the technology behind the sensor makes it much easier to fabricate, and its resistance to shock and damage. Of course, it doesn't mean it cannot be crushed. It can be crushed, but it's tough. You know, if you look at the prototype designed by the company in Michigan, it's got low noise, it's got good immunity from external electromagnetic fields, flexible size and shape. That's one of the things we found. We found out that the size is very flexible. We can make it small, we can make it big. All depends on the application. For example, in the commercial application, like using cell phones, we can make this sensor very small because we don't need high random walk per hour value, and therefore we can make the sensor very small with low concentration of nanoparticles. Whereas if you go to the military side, where you need a quality, talking about 10 raised to minus 3 degree per hour, the quality is paramount, and therefore you need to have a better concentration of nanoparticles, better shape, etc. One thing we still don't know is we don't know the minimum size, but we know that we can get flexible size and then we can get flexible shape. Disadvantages, it requires high accurate AC signals and AC measurements, very, very important. Presently, what we are using on our test bed is we are using AC generator to do the, to split into two to get the two signals we need. But we are working towards DC, where we shall use DC to AC converters to build better AC systems that we know will give us better control over the phase angles, and then of course give us better AC signals. And of course we know that almost all sensors use DC supplies, and so we have the DC there, except now we've introduced power electronics to take the DC to AC. Now, one thing though is that the magnetic nanoparticles are relatively expensive. We bought 5 milligram per milliliter for about $1,000. Even though we could mix them up with the mixing solution, the ethylene glycol, we could make different concentrations from that one we bought. I think we made about three concentrations for the one we bought, but it's still expensive. But the good thing is that for low applications or for commercial applications where the random walk is not that low, we can make low concentration of nanoparticles and therefore reduce the cost, even though the cost of that nanoparticle concentration is originally very high. By making extra concentration from the ethylene glycol, we could make more solution concentrations from that one we bought. Thank you. Questions?